We will now discuss matched filter, but before going to the actual general description of matched filter, we will take an example of matched filter. Matched filter may be of different type. One of the example of such matched filter is the dump and integrate filter. So we will first try to understand the dump and integrate filter, and once we can understand this dump and integrate filter, we will go for the general description of the matched filter. Suppose the noise is Gaussian and therefore the noise voltage has probability density which is entirely symmetrical with respect to 0 volt. Then the probability that the noise has increased the sample value is the same as the probability that the noise has decreased the sample value. We can assume that if the sample value is positive, the transmitted level was plus V, and if the sample value is negative, the transmitted level was minus V, assuming it is bipolar signaling. It is possible that at the sampling time, the noise voltage may be of magnitude larger than V and of polarity opposite to the polarity assigned to the transmitted bit. So, what happens if we have transmitted highly defined pulse like this at the transmitter up to say T1 to T2, but at the receiver what we are getting say this type of signal, because along with the signal there will be some noise. And what happens when we take the sample? Say we are taking the sample at this time. So at particular this time the signal value was V, but the noise voltage was more than V and in the opposite direction. So if we take the sample, instead of getting positive voltage, we will get some negative voltage, and our decision will be that since we have received negative voltage, our decision will be in favor of minus V volt, which is an error. We can reduce this probability of error by processing the received signal plus noise in such a manner that we are then able to find a sample time where the sample voltage due to the signal is enhanced relative to the sample voltage due to the noise. So consider now the dump and integrate filter. Circuit. So this is the circuit for dump and integrate filter. The input signal is given in this way. Maximum voltage is V, and up to time t, 0 to t is the bit time. Now in the channel some noise will be added, and we are assuming it is a white noise, and its PSD is given like N0 by 2. This is the main integrator part, consists of R and C and a amplifier. An amplifier is there. Along with this basic integrator, we have two switches. One is the dump switch S1, another is the sample switch S2. Here the voltage is say V0 and the output is V0 at time t. Since we are taking the sample, we will get the discrete voltage here, discrete samples here. So this is the basic circuit for the dump and integrate filter. Now the signal ST with added white Gaussian noise NT of this given PSD of N0 by 2 is presented to the integrator at time 0 plus, just after giving the signal here, we require that the capacitor C be uncharged completely, and such discharged condition may be ensured by a brief closing of switch S1 or dump switch. So momentarily we close this dump switch S1 so that the charge present in capacitor will be discharged or neutralized. Now that should be done before giving the actual signal. That means at exactly time t equal to 0, this capacitor must be at 0 condition. So we can say in this way, at time 0 minus, t equal to 0 minus, we will momentarily close this switch S1 so that charge is neutralized, and then we will present the actual signal here. Thus, relieving capacitor C of any charge, it may have occurred during the present interval, because we are just assuming as if we are we are observing this at the midpoint. That means there are some previous bits and there will be some bits later on will come, other bits will come in future. The sample is taken at the output of the integrator by closing the sample switch S2. This one. The sample is taken at the end of the bit interval at time t equal to capital T, at the end of the bit period. The signal processing is described by the phrase integrate and dump, referring to the abrupt discharge of capacitor after each sampling. That is why it is called dump actually. Now integrator yields an output which is the integral of the input multiplied by the time constant 1 by RC. So here the time constant is tau equal to 1 by RC. So we can write V0t, the final output, 1 by tau equal to RC, 0 to t st plus nt dt, that is equal to 1 by tau 0 to t st dt plus 1 by tau 0 to t nt dt. Or it can be written as, this one is the output signal part and this second part is the noise part. So this is the sample voltage due to signal, this is the sample voltage due to noise. The variance of N0t given as equal to N0 by 2 t by tau square. So S0t equal to 1 by tau 0 to t v dt, that is equal to v into t by tau. So this is the output signal part, and this is the variance of the noise. So if we draw the corresponding output due to signal part and noise part. We can see that, say this is our time of pulse, say, and this is indicating that the voltage output signal will vary depending on the time. It is proportional to time. This is the maximum value at time capital T, but actually it is varying as if in a ramp fashion. So it will increase in this way at time up to time capital T. So this peak voltage is Vt by tau here. This voltage is Vt by tau. So this is the signal part, and we will take the sample at this time. Then we will switch on the dump switch. So it will fall here, and then again next beat will start. Now what happens to the noise during this time? This is the N0T. It will also start from 0 because of the dump switch is closed, so the capacitor will not carry any charge, so it will start from 0 again. Now N0 is random, I mean input noise is random. So if we integrate this N0 input noise, then it will also be random. That means output noise is random. So it will change in the similar fashion as that of the almost similar fashion as that of the input noise, something like this. And again for the next bit period it will fluctuate in this way. That means this N0T is not integrated because, or the integration voltage is not will not increase because n is the random. That means it is uncorrelated, so it will not increase. This integrator will not be able to increase its voltage value. But for the signal is correlated, so its voltage value will increase in a ramp fashion. So once we take the sample, once we close the sample switch S2 at this time, we will get the signal value Vt by tau and the noise value N0T. So V0T will be equal to, that we have already said here, we have already written this thing, S0T, this is S0T, Vt by tau, and this is N0T. This one is N0T. So we would naturally like the output signal voltage to be as large as possible in comparison with the noise voltage. Hence the figure of merit of interest is the signal to noise ratio that we can calculate as S0T whole square by N0T whole square equal to 2 by N0 V square into T. And you can see that the signal to noise ratio increases with increasing bit duration T, and that it depends on V square T, which is the normalized energy of the bit signal. Now we will consider the probability of error. probability of error for damped integrate filter. Probability density of noise f n0 t, assuming it is Gaussian in nature, we can write 1 by root over 2 pi sigma 0 square exponential minus n0 square t by 2 sigma 0 square. So it is a conventional bell-shaped characteristics like this. And we set the threshold, say right here, Vt by tau, that is the maximum signal value. Under this condition we will try to get the probability of error. Now when the error will occur, the error will occur when the noise voltage is greater than Vt by tau, where Vt by tau is the maximum signal voltage at the output when we take the sample. That means when noise becomes larger than the signal part, output signal part, then only the error can occur. So this area will give us the amount of error. So probability of error for damped and integrate filter can be written as Vt by tau f n0 t dn0 t. Putting the expression of f n0 t from here, you can write Vt by tau to infinity to minus n0 square t by 2 sigma 0 square divided by root over 2 pi sigma 0 square dn0 t. Now let us assume x equal to n0 t by root 2 sigma 0. Putting this in the expression of PE, you can write 1 by root pi x equal to v root over t by n0 to infinity e to the power minus x square dx, which is the complementary error function with the argument of v root over t by n0. Now we change the argument little bit, v square t by n0 whole to the power half, that is half of es by n0 to the power half, where es is the bit energy, v square t equal to bit energy. So the probability of error is given by this equation, and if we plot it, we will get this type of characteristics, just like waterfall. With Es by n0, it will change vary like this. So PE decreases with increase in Es by n0. Es by n0 is nothing but a kind of signal to noise ratio. That means signal to noise ratio and the bit error probability are linked to each other. So even if the signal is entirely lost in the noise, so that any determination of the receiver is a sheer guess, the receiver cannot be wrong more than half the time of the average, on the average. So this is the bit error probability for dampened integrated filter.